Okay, so our second speaker of the session is Karyn McLellan. She's an assistant professor of mathematics at Mount St. Vincent University in Halifax. So please.
Great, thank you. Thanks for the chance to speak. So I'm going to be talking about an interesting little problem, looking for Fibonacci numbers in sets generated from linear operations. So it's not super complicated in terms of the computation that was involved, but there's a conjecture that I'll tell you about, and we use some calculation to help us solve the problem. So the first part, I'll tell you what the problem is, and then look at some patterns that helped us to solve the problem. So this was a problem posed at the 16th Fibonacci Conference in 2014 by Clark Kimberling. So we have some set S of integers, and we imagine we start with number 1 in the set S, and then for any element x in the set, we also add in 2x and 1 minus x. So the idea is that S, we can think of it as growing in generations. So if we start with G1, which is the set containing 1, we can take 1, we can double it, and we can do 1 minus, and that will generate new elements. So if we double it, we get 2. If we do 1 minus 1, we get 0. That gives us 2 new elements that we'll call G2. And we obviously keep doing this. So we can take G2 and double anything in there. That gives us 4. We can do 1 minus anything in there. So 1 minus 2 gives us the negative 1. 1 minus 0 gives us 1, but 1 already appears in G1. So we're only adding in new elements to the set. So the problem is to prove or disprove that every generation contains at least one Fibonacci number or it's negative. So we're going to call these sets GI, generations, or generation I, where I is the index. And we'll note that these sets GI are pairwise disjoint. So we're only looking at new elements that are added to the set S. So S itself is the union of all these sets GI. So we sort of took a step backwards. Instead of starting at 1, we started at 0. It just shifts a little bit in the beginning. And you can see these are the first 7 generations here. So we saw the first few. Again, the first couple are changed a little bit if we start at 0, taking that step backwards. We saw up to negative 1, 4. Let me see if this laser works. I guess I don't remember. Top button, thank you. Yeah, negative 1, 4. So again, we can think about taking these numbers. We can double them to get negative 2 and 8. 1 minus 4 gives us negative 3. But 1 minus minus 1 gets us back to 2. So it's not a new element. So we keep doing this and generating these sets. And the idea is we're looking for, do these sets always contain a Fibonacci number or a negative of a Fibonacci number? So you can kind of see in bold. We have 1, 2, negative 1. These are all, or have that Fibonacci, where to go? I don't really need it, I guess. Kind of dying. G4, negative 3, negative 2, 8. Those are all either Fibonacci's or negatives. Then we keep looking. If you can see the numbers in bold, at least up to G7, all of these have either a Fibonacci number or it's negative. So does this always hold, is the question. And why would it hold? So it makes sense to think about this in terms of a tree because we have 2 operations. So if you look at, we have 0, 1. Once we get to 2, you can see that it branches off. So we're going to let the left children be the 1 minus operation and the right children be the doubling operation. So I'll come back to this in a second, but some of the structure in the tree that we can see, kind of as I mentioned, is that here, any even elements, so if we look at this bottom row, any of the even numbers clearly come from doubling everything in the previous row. So negative 2, negative 3, negative 8, we double those all to get the circled elements. And then any odd children, like in the bottom row, they do come from 1 minus things in the previous row. But if we jump back 2 rows, we can think about those as coming from subtracting the double of all terms 2 rows back from 1. So we're kind of just combining 2 operations there. So the reason we can do that is because then we can think of everything, say, in this bottom row as being an operation on the row before it, plus some other operation on the row before that. And notice that we never apply the 1 minus x operation to any of the odd numbers. Let me try this one more time. Yeah, there we are. So you can see that, for example, here, if we did 1 minus minus 3, there's no child here because that would just take us back to the parent 4. So we never include, you can see all these numbers are unique. We don't include these doubles so that the right children always have 2 children, but the left children in a tree only have a right child. So this kind of structure, you can probably see, is going to give us a Fibonacci number of elements in each row. So this is just a simple induction. The first two generations had one element, and then we, from these operations that we talked about, everything in the previous row gets doubled. Everything 2 rows back, we do 1 minus the double. We add those up, and we can see that it has this sort of Fibonacci relationship. So if we go back a little bit more, you can see again that if you start counting, each of these sets contains a Fibonacci number of numbers. So we're not necessarily looking at what the numbers are yet, but just the sizes of these generations. Okay, we'll skip ahead. So then the number of terms in each row is then growing approximately the rate equal to the golden ratio, right, which is the rate of growth of the Fibonacci numbers. So we generated a little further than just those 7 rows. Okay, first by hand, then wrote a program, and we didn't find any counterexamples for at least a short search. So then we thought, okay, maybe this is actually true. So let's look at some other methods to figure out if it's true. Why is it true? So the first few questions we asked then are, okay, what numbers do actually appear in this set? And where do they appear in the tree, right? So you can see these numbers in different generations in the tree. Where do particular numbers occur? Okay, because of course we want to think about where do the Fibonacci numbers occur in the tree. So the first theorem is that all integers actually do belong to the set S, so all positive and negative integers. And this is just a simple contradiction. If we assume that some integer k is not in the set, we can trace a decreasing sequence in absolute value of uniquely appearing integers backwards all the way to the node. So if some k wasn't there, everything that came before it couldn't be there, including the node, and then we get a contradiction. So we're able to see that every integer does belong to the set S. So that led us to thinking about, okay, well, where do these numbers occur in the tree? So this table, you can see it's kind of in groups of 4. So the k here, the k's are the integers, so 1, -1, 2, -2, 3, -3. And in the column next to it, I, this is the row in which you can find it in the tree. So this sequence that's bolded, 0, 1, 3, 2, 4, 5, 4, 3, 5, 6, 7, gives us kind of a nice sequence that tells us where we can find these integers in the tree. So of course, the first thing we did was check if it was in the OEIS, and it wasn't. It's there now, but it wasn't when we first came up with the sequence. So this is kind of an interesting sequence. You can see it's going up and down by 1s and 2s. So maybe if we could understand the nature of the sequence, we can figure out exactly where all the integers are appearing in the tree. So we'll go over some of the patterns that are in the tree, because this is kind of, we can completely determine what's going on with this sequence. And everything is in groups of 4, because we're going to be looking at some things mod 4 here. Okay, so I think there's 5 theorems that tell us exactly what's happening in the tree, okay, broken down into specific cases. So when we're looking at a negative odd number of the form 1 minus 2L, and then jumping in the table to a positive even number 2L, the generation index decreases by 1. So I think I have that here. So you can see, again, if we're looking at, say, -1 and then moving up to 2, -1 appears in row 3 of the table, 2 appears in row 2 of the table. And that's the case anytime we go from a negative odd number to a positive even number. So these numbers in red, you can see these are the generations. So we're going from 3 to 2, 4 to 3, 7 to 6. It's always decreasing by 1. And there's nothing really that complicated here. If we just look at the operations of how these things are generated, if we start with some positive number L, the next row we get the double, and then the next row after that, we get that 1 minus operation. So if in the table, we're starting at the 1 minus 2L, and then the next thing in the table is 2L, well, that generation index is 1 less, or it's decreasing by 1. So we can go through a bunch of these patterns. The next one is if we're moving from an even, negative even number to a positive odd number in the table. So for example, like -2 to 3, or -4 to 5, we're increasing by 1. And we can look at the tree and see the proof of that in a very similar way. So it's kind of looking at 2 rows at a time in the table here. The next one is if we're moving from a positive odd number k to its negative in the table. So again, you can see here we're going from 3 to -3, or 5 to -5, 7 to -7. These numbers in red, sometimes they go up by 1, sometimes they go down by 1. And that's dependent on the value of k mod 4. So you can see that when k is 3, here, well, it's 3 mod 4, we're decreasing by 1. When k is 5, it's 1 mod 4, so we're increasing by 1. And they kind of alternate. So whether those numbers are going up or down by 1. It's 2 more. So the next one is if we're looking at even numbers that are not powers of 2. So if we take some even numbers and we factor out any powers of 2, leaving us with some odd m, this is again dependent on the value of, this time, m mod 4. So if we look over here, when k is 6, okay, if we're going from 6 to negative 6 in the table, if we factor out a 2, we're left with a 3, which is 3 mod 4. So this tells us we're getting a decrease by 1. Or if we look at 10, we factor out a 2, we're left with 5, which is 1 mod 4, we're getting an increase. So again, we can see in the case of even numbers that are not powers of 2, we're getting increasing and decreasing again. The very last case is what happens with the powers of 2. If we're going from, say, 2 to negative 2, or 4 to negative 4, 8 to negative 8, we're getting a jump by 2. So everything else is kind of going up or down by 1. Here we have a jump of size 2. So all of those patterns together are going to tell us exactly what's happening in the table, so we can keep generating the sequence and see where all these numbers are actually appearing in the tree. But we're not interested in all the numbers, really. We're only interested in the Fibonacci numbers. So, and we don't know if this is true or not. We don't know if we haven't found a counterexample yet. So what we ideally want to do is come up with some kind of a formula for this sequence. So some kind of expression for the sequence. So what we're going to do is kind of redefine things a little bit. So we're looking for integer k, and we're going to introduce an n, so it's easier just to look at the table here. So and we're looking at 1, negative 1, 2, negative 2, 3, negative 3. We're just going to index that by n. So k is the number, and n is where it's found in the tree. So generation 0, 1, 2, 3, 4, 5, etc. So that k and n are related. K and n are related via this expression that you see here. So for example, if we look in the table, k equals negative 5. You can see it in this bottom row here. That's like the 10th term into the sequence. So that means that f of 10 is 7, meaning negative 5 occurs in the 7th row of the tree. So we want some formula for f of n. That's the goal. So if we can find that, that might help us to figure out exactly where the integers are appearing. So the first thing we did was like a lot of playing around with this sequence to figure out how it works. But one thing we did was to look at the difference sequence. So just the sequence we had bolded before, if we look at the difference between any 2 consecutive terms, we get this new table. And this kind of does exactly read off those patterns we talked about before, where we're increasing or decreasing by 1. Sometimes we increase by 2. That occurs where the index is a power of 2. So what about this sequence? Is this anything? This was not in OEIS either, so nothing known about this exact sequence. However, there were some similar sequences if we tweak this just a little bit. So what we thought to do is to get rid of the 2's. We know where these 2's appear. If we divide out all the 2's, we'll generate a new sequence that we'll call A sub d of n. Okay, so this is just telling us A sub d of n is the same as f sub d. Sorry, I should have said f sub d is what we call the difference sequence, subtracting these terms in f. If we modify it slightly by dividing out the 2's, we get this new sequence A sub d of n. So exactly the same as the other one, except we replace the 2's by 1's. Is this sequence known? Yes, this one was an OEIS, which is nice. So we're hitting on something known. What is the sequence? It actually is the Jacobi symbol for negative 1 over n, which is nothing at all related to what we're doing, but it's a known sequence, and it was given actually by this recursion, which is kind of nice. And we can actually verify based on the patterns we already found that yes, this does actually match our sequence. We can prove this holds based on those theorems 3 through 7 we just looked at. So we do have some kind of a recursion happening here, some kind of a known sequence. Also, interestingly, so if we go back and have a look, this is all 1's and negative 1's. This is an even more well-known sequence if you take the negative 1's and replace them by 0's so that we get a binary sequence. This actually turns into the regular paper folding sequence, also known as the dragon curve sequence. So you've seen this picture here probably, right? So this is the picture. It's a nice fractal. that you get if, I think if the ones represent a 90-degree turn to the right and the zeros are a turn to the left, and you trace the sequence out, it forms this fractal-like structure. If you've read the book Jurassic Park, these pictures are in each of the chapter titles in increasingly more complex fractal forms. So this cool sequence we found now has some connections to this known fractal sequence. But what does this actually tell us? How does this help us compute this? So just to recap, we started with this sequence f of n that tells us the location of any positive or negative integer in this tree that we developed using two operations. We looked at the difference sequence, f sub d of n. We divided out the powers of 2 to get this new sequence that we called a sub d of n. And now we're going to go backwards again and take partial sums of this sequence. So we're going to take this a sub d and then just add up the partial sums to get kind of an analogous sequence to our original sequence f. And it looks like this. So again, we're just adding up the consecutive terms to get a of n. So this a of n is almost the sequence we want, except it's a little bit smaller because we took out those powers of 2. So it's not growing quite as quickly. But the nice thing is that this sequence was also in OEIS. So this is going to help us to actually calculate the thing that we want. So what is this sequence? Well, it turns out that this sequence is the number of runs in the binary expansion of n. Also, it's the number of ones in the gray code of n. So what does that look like? So the nice thing is that when we're talking about the number of runs in the binary expansion, all of a sudden this is not recursive anymore. So if we wanted to calculate f to some large values of n, to either try to prove this theorem or look for a counterexample, we can now calculate it without having to go through every step along the way. So if we look at, here's our integers k again, here are the n's, just the index, and here's our sequence a of n that we just found. So the number of runs in the binary expansion, so here's the binary expansion of our n's here. It's just telling us sort of how many distinct groups we have of zeros and ones. So for example, here we have n is 5, binary is 1, 0, 1. So we have 1, 1, 1, 0, and 1, 1. So there's 3 different runs, where 4 is 1 followed by 2 zeros. So 1 is a run, the 2 zeros are a run. So we have 2 runs. Or if we go down, 1, 0, 1, 0, that has 4 runs. So we're just calculating that for each of the n's, and that actually gives us this a of n sequence. So we're kind of following this path through some different sequences to get what we eventually want, which was that original sequence we started with. It told us the location of integers in the tree. So an almost gives us fn. The only difference was we had divided out those powers of 2, so we need to add them back in. So basically the sequence we want, f of n, is a of n, which is counting these binary runs. And then if we add back in the powers of 2 we took out, this is just the floor of log 2 to the n, log 2n. So again, just remembering how n and k are connected. N is just the index, but k is the actual integer that we're looking for. So again, another table to kind of summarize all of this. So here was this a of n, which is the number of runs. We add back in this log term, and then we get the sequence we're looking for, f of n. So now this is something that's fairly easy to calculate these values of f of n without having to do it recursively, which is what we want. So what does all this tell us then about the original problem? So there is a counterexample that we found. And again, remember, we're interested in which generations contain a Fibonacci number or it's negative. So we don't care where all the integers occur. We're only looking for where are those Fibonacci numbers. Okay, so the following table, this gives us the location, i.e. the generation index, for the first 64 Fibonacci numbers and their negatives. Okay, so we included 1 twice just because the Fibonacci sequence 1, 1, 2, 3, 5, 8. The next row would be like 13, negative 13, 21, negative 21, and so on. So it's telling us where in the tree these numbers occur. So we were able to calculate this now that we had this sort of nice relation with the number of runs. And we didn't have to calculate this recursively for all of those integers in between. We're only focusing in on those Fibonacci numbers. So if we want to know Okay, does every generation contain a Fibonacci number? Well, these are all the generations here where at least these first 64 Fibonacci numbers and their negatives live. We need to look if anything is missing. Okay, so if you scan through and start looking for all the numbers, you'll find that the first number that's not here is 43. So we have 40 and 41 and 42. And I know it's going up and down a little bit, but at least up to this point, there's no 43 in this table. So that's our potential counterexample, that at least in the first 64 Fibonacci numbers and their negatives, there's no 43. Or 43 doesn't contain one. So 43, 47, 53. So there are a bunch, but we want to make sure that those numbers aren't going to arise a little bit later in the table. So if we go back, it looks like by the time we get down in this table, we're up into the 50s and 60s, and it doesn't seem like it's dropping back down that much. It doesn't look like we're going to get a 43 from this point onward, but we want to be sure of that, of course. So the counterexample is that the 43rd generation does not contain a Fibonacci number or it's negative. So here is our formula that we were using, a of n plus the floor of the log function. A of n was, remember, was going up and down a little bit, like up and down by 1. So it's not increasing nor decreasing. However, this log function is non-decreasing. So it's going to provide a lower bound. It's kind of a crude lower bound, but it works. So we know that f of n is always greater than the floor of the log function. So if we think about the first 64 Fibonacci numbers and their negatives, here is f64, which is this really big number here. So that gives us in the sequence, the index is n is equal to 2k minus 1. That's where we find it in the sequence. Log 2 of n is 44. So what that means from the previous table, we saw that of the first 64 Fibonacci numbers and their negatives, none of them occurred in generation 43, but this is telling us from this point onward, the lower bound is 44. So we can never get back down to 43, meaning that 43 is actually going to be a proper counterexample. So in the table, we never have a Fibonacci number occurring in generation 43. So in terms of thinking back originally, if we were to do that out just by calculating the tree, that's the 43rd row of the tree. The 43rd Fibonacci number is 433 million. So it would have been kind of difficult to calculate this by brute force. And even using this f of n recursively, we kind of knew how the sequence behaved, but calculating all the way up to so even the 64th Fibonacci number, that's pretty far to go if we had to calculate it in a recursive way. So at least by calculating these runs, using the number of runs in the binary number, it was pretty easy to calculate this table and find the counterexample. There's another nice little recurrence for f of n as well. But again, it's still a little bit cumbersome to use because we're interested only in the Fibonacci numbers and nothing in between. So we could kind of cut out all that middle stuff. So just to finish up, the question we had was, okay, well, we found a counterexample. Clearly this wasn't true, but it was true at least far enough that it seemed like it might have been true. The people that posed the problem didn't get as far as finding a counterexample, but how often do these occur? So there's a bunch of generations that don't contain any Fibonacci numbers, you can see here. And of the first 5,000 Fibonacci numbers can be found within the first 3,741 generations in the tree. Of these, 509, which is about 14.6%, don't contain a Fibonacci number. So they're really not that rare at all. It just took a while to find one. If we keep going some more generations down, we're still around this 14.6, 14.7% of generations don't contain a Fibonacci number. So maybe there's really nothing special about the Fibonacci numbers of why they would or wouldn't occur now that we've kind of shown that this isn't true. But we thought we'd try looking at some generalized Fibonacci sequences as well. So instead of starting with 1, 1, if we start with initial terms 1a, and then we looked at where numbers in that generalized sequence appear in the tree for a between 1 and 12. Okay, so 12 different sequences. We found that, again, between 13 and 15% of generations fail to contain a number in such a sequence. So that's basically it. It was just like a fun little problem that we picked up at a conference, and it kind of led to some interesting results, I think, particularly with sort of the fractal nature of where these numbers occur in the tree, even if the original conjecture wasn't true. So that is everything. Thank you very much.